Okay, let's continue with the second page of our problems from last week, actually. These are the second page of the 2018 Regents questions for the June Regents test. Number 11 is a picture, and pictures are fun, but you got to look at them carefully because sometimes they'll put extra stuff in there that you don't really need. This is a picture of an inclined plane, like a slide, and something set on the inclined plane, which is a box or who knows what, doesn't matter. And this object has some forces that are going to be acting on it. Their forces, the obvious force is going to be gravity, which pulls it straight down like this, vector c. So gravity is always from the center of the object directly to the center of the earth. So notice that it makes an angle with the inclined plane, not a 90-degree angle either. The normal force is the force of the inclined plane pushing up on the box. If that force didn't exist, the box would fall down to the ground. If you tried to slide a 50-pound box on a piece of cardboard, thin cardboard, on a ramp, it'll just squish the cardboard. So the normal force has to be provided by the surface on which it's sliding, and that surface has to be significant enough, strong enough to support the box. But that one then is the force A. There's a weight force that pushes against force A. Weight force would be part of this gravity force, but not all of it because it's at an angle. But that's more detail than we need on this problem. And then there's two other vectors given to us. B is a vector which looks like it's some kind of a force. Notice as I look at this, I had to stop for a minute and read the question. Which arrow represents the direction of the force? So these vectors are forces, not velocities. They show a velocity up here because the velocity is not the same type of vector as these guys. These are all forces. The gravity force down, the normal force up. This is basically the force, the net force that's making the box slide down the ramp, and this force is opposing that force. So, and they give us the velocity. It says which arrow represents the direction of the frictional force acting on the box. The definition of frictional force is it always opposes or tries to the motion. So if this thing is not moving, there'll be a frictional force, and that frictional force would be big enough to keep it from moving. If we make the ramp big enough angle, or the weight big enough, or give it a shove, then we'll have a force downward and a friction force backwards. Friction force always opposes motion. So you don't really have to overthink this question. You would say motion is down on B because it's showing the velocity up here. So friction would oppose it, and the fact that it's going up the ramp is fine because the box is sliding down the ramp. Friction opposes motion. And there's always some problems like this on Regents questions. You don't have to do a bunch of components of vectors and all that. You just look at it and say, friction is going to, it is moving, so I know it's going to be kinetic or moving friction, and it's going to oppose the motion. So D. Okay, and next one, another picture. When you get a picture like this, you got to look at it. What the heck are they trying to show us here? It says, which diagram represents the directions of the velocity V and acceleration A of a toy car as it moves in a clockwise means the way an old-fashioned clock goes around like this. Clockwise, horizontal, circular path at a constant speed. Okay, constant speed is important. That means it's not accelerating. It's not slowing down or speeding up. It's going around the circle. And we would actually call that the tangential velocity. If the car were to break loose from whatever's making it go in a circle, or the steering wheel stopped working, the car would shoot off straight, a tangent line to this circle. So the speed is what we call tangential velocity. And remember, velocity has two components. It has a direction and a magnitude. And if you change either one of those, or both, then you're accelerating. And acceleration is a change of velocity, and velocity is a direction and a magnitude, which we can also say is a speed. So this guy, we have the center of the circle here, and the car is going up toward the right, or the top of the page here. And something's making this car turn as it tries to go straight, turn and stay going in a circle. And the only thing that could make that happen would be some kind of an acceleration toward the center of the circle. We call that centripetal, which means center-seeking acceleration. So there's some force which is being provided by the tires of this little car that's making it turn, so the speed stays the same, but the direction is changing, so it is an acceleration. Okay, so this diagram's right. That's the answer. What's wrong with this one? Well, it's showing an acceleration this way, which would make the car speed up, and they say constant speed. A velocity this way would shift the car over to the right, and that doesn't even make sense, so no, it's not this one. This guy has acceleration, again making the car go faster, and the velocity shifting it off to the left. That doesn't make any sense. And this guy has acceleration this way. This would make the car go in a circle like this. So don't overthink this one. We have to have a force directed toward the center, an acceleration producing a force, and the velocity that way. So that's the right answer. Got it? What did I write on here? The speed of the car going around the circle is not changing, the speed, but the direction is constantly changing. Change in direction is acceleration. Change in speed is acceleration. Change in both is acceleration. Change in neither one is not acceleration. Okay. Let's move this over a little bit, if I can. We're good. It says a charged particle, like a little piece of dust, is located in an electric field. Electric field is the energy field that spreads out from something that has an electrical charge. Old-fashioned TVs that had the big picture tube would have an electric charge when you turn them off, and if you put your hand over there by it, you could feel it. So electric field is just the energy coming out of an object that has a charge, and it's not really energy, it's a field force, but we'll just say it's something you can sense. Okay, and if you were doing this on a Regents test, at this point you'd probably want to look up the equations for the electric field intensity is this guy, E, and it's a vector quantity, that's what that thing is for. E is equal to the force on a charge divided by the charge. If I want to test a gravity field, I want to test how strong gravity is, I drop something in it. So if I wanted to test a gravity field, I would take the force on the book divided by the book's mass, and I could get the gravitational acceleration. So the way you test a field is put something in the field that can respond to it. A mass can respond to gravity, a charge can respond to electric charge. I wrote this and then I rearranged it. The force divided by the E vector is equal to Q. That's not a 9, that's my Q. I'm Q challenged. So then I got the numbers on here. They say the magnitude of the electric field strength is this guy, 2 times 10 to the third. That's this E guy, which is on the bottom here. And the magnitude of electrostatic force is 3 times 10 to the minus 3. So here's the force up here. And don't try to do this in your head. Just do it in the calculator, because exponents, when you're dividing them, can be kind of weird. And when you do this, then you're going to get a 3 minus 3, which is for the exponent, it will be minus 6. 1.5 times 10 to the minus 6. And the unit is coulombs, because we have newtons on the top here and newtons per coulomb here. So we flip this one upside down to divide it, and these guys cancel out, so we get the unit coulombs. Okay. Next one, the magnitude, the size of the gravitational field strength near the Earth's surface is represented by, you can actually do this a couple of ways, but just take the simplest way. We say weight is equal to mass times gravity is one thing, and we also say gravity, that means gravity is the force of gravity divided by the mass, just like this one on the top here said the charge was the force on the charge divided by the gravity field, well, in that case the electric field. Let's not mix up problems. Okay, so I wrote weight is equal to mass times gravity, and that's then solved for G, F over G over M, and that's what's the answer. It can't just be G. G is the gravitational constant. Mass times gravity is the weight, but that's not, the weight is not the magnitude of the gravitational field. The weight is not the same as the gravity acceleration. The weight is what's happening because of the gravity acceleration. And this is just Newton's law of universal gravitation, which we could use if we put g, the constant, and mass 1, the mass of the object that we're talking about, and mass 2, the mass of the Earth, and this, but we don't have to do all that. It's just F sub g over m. Okay. Next one's a little involved. Number 15. Hey, we're almost done, guys. A car engine supplies 2 times 10 to the third joules of energy during the 10 seconds it takes to accelerate the car along a horizontal surface. It means we're not going uphill or anything. What is the power developed by the car engine while it is accelerating? Power is the rate of doing work. So the units for work are joule, and a joule every second gives me a certain amount of power. So power is measured in watts. Like a 50-watt light bulb uses a certain amount of power. All right, so it says, what do we got here? We have this many joules of energy in 10 seconds. So just given the number, you just got to figure out where to put them. To put the energy on the top, because it's right there. Energy and work have the same units, joules. Energy on the top and the time on the bottom. And then you get 200 watts. Duh, and that's the answer right here. We didn't do as many of these problems as others, so if you saw that, you'd probably get scared and freak out, but it's not worth it. Okay, if you got number 16 wrong, I'm going to put you back in Matter and Energy 101. Which forces can be either attractive or repulsive? Well, attractive forces would be magnets. You've seen magnets stick together, and you've seen magnets repel each other. Electric forces can do the same thing. They're not as easy to produce and play with as magnets, but gravitational forces can only attract. If you can invent an anti-gravity or a gravity thing that repels, you'll be rich and famous, because that'll be a great way to move stuff and have people fly and transportation, all that good stuff. That's your challenge once you get out of high school, then college. So, which force can be either attractive or repulsive? Well, number 1 is not correct because it's gravitational. That can't be. Number 2 has gravitational. It can't be. Number 3 is the one that we want, magnetic and electrostatic. And number 4 has gravitational again. That one is just a process of elimination. Okay, let's see. This one I probably get wrong too. It's a hard question. Number 17. There's 2 things when we talk about resistance. Resistivity is a property of the metal that's conducting the electrical current. Different metals have different resistivities. There's a table of resistivities in your reference packet for physics. Resistance is just the effect of resistivity on a current. Not the same thing, but it starts out with the same word. Okay, so it says resistivity of 4 meter length of 1 millimeter diameter copper wire. Well, you could look up the resistivity of copper wire if you needed to, but you don't really need to. We're just doing a comparison. We have 40 centimeters, 0.4 meters, and it's 1 millimeter diameter, and it's at 0 degrees centigrade. And the second one is a 0.8 meter, and everything else is the same. 1 millimeter, and it's basically at 0 degrees centigrade the same. So then we start thinking of 1/4 and 1/2 and all this, and my dog just walked in dropping toys on the floor. Okay, so the question is, compare the resistivity of this short piece to the long piece, and the resistivity is just a function of the material. It doesn't change. So the answer is the same. It's the resistivity of copper. It doesn't change no matter how long the wire. But this dog doesn't give up, does he? That would be resistance if we were looking at a circuit. Okay, last question. The work per unit charge required to move a charge between 2 points in an electric circuit. This is just kind of a definition. And if you were awake the day we talked about electricity, you'd probably get it, but otherwise you'd have to make a wild guess. But force, power, those ones we know are not really related to an electric circuit. Field strength would not be an electric circuit. That would just be like in the air. So, but electric circuit, potential difference. I already said potential is the same as voltage. So that's the answer for that one. Okay, that's why we're going to have another sheet to do next week. And we'll be doing 2 of these for the next 2 weeks. And then a lot of these questions are going to be on your final. So I suggest you print out this sheet if you want to, so you'll have a hard copy of it. They're the ones that I'm showing on the screen are already posted on the website, and I'll do that with the others after I collect the grades and see who did them and turned them in. If you don't do them and turn them in, you'll get some score like a 6 out of 10, so you don't get screwed. Unless I've made arrangements with you otherwise, you still have to do the papers. But anyway, hope you have a good weekend. I guess I got one more thing to do. Try to get to the lab, and that's the last lab we're going to do. Take care.